Welcome back, everyone. In this lecture, we're going to have a brief overview on scikit-learn. We've just seen that NumPy had some built-in capabilities for simple linear regression using the np.polyfit function. However, when it comes to more complex models, we're going to need the full capabilities of scikit-learn, the most popular machine learning library for Python. Before we jump straight into machine learning of scikit-learn in Python, however, let's understand the philosophy behind scikit-learn, or the way it looks when you import it into Python, sklearn. Scikit-learn is a library containing many machine learning algorithms. And the most important factor of scikit-learn is that it's utilizing what they call a generalized estimator API framework in order to call and use the various models that we're going to be creating. And internally, scikit-learn refers to all the machine learning algorithms as estimators, because at the end of the day, all a machine learning algorithm does is estimate some output. Now, this means the way the algorithms are imported, fitted, and used is uniform across all algorithms. So whether you're running a linear regression or something more complex like a random forest application or algorithm, the way you actually import them and use them is going to be extremely similar, regardless of what algorithm you're using. What's nice about this approach is it allows users to easily swap algorithms in and out and quickly test various approaches and various algorithms and models. An important note that also corresponds to this particular framework feature is that the uniform framework is so easy to use, it means users can easily apply almost any algorithm, even sometimes effectively, without truly understanding what the algorithm is doing. That's why it's so important to take the time to try to understand the theory and intuition behind what the algorithm is doing, because you could jump straight to scikit-learn and apply these algorithms, see good results, and not truly understand what is actually happening. Scikit-learn also comes with many convenience tools, not just machine learning algorithms. It includes things like train test split functions, cross-validation tools, and a variety of reporting metric functions to analyze model performance. This leaves scikit-learn as a one-stop shop for many of our machine learning needs. Now let's talk about the philosophy behind scikit-learn. In general, scikit-learn's approach to model building focuses on applying models and performance metrics. Essentially, we're going to train a model on some data and then check its performance on a set of data that it hasn't seen before, at least for supervised learning. And this is a more pragmatic industry-style approach rather than an academic approach of trying to build out a model and then really focusing on those model's parameters, as well as the way the model can actually describe the underlying data set. Instead, scikit-learn is really focused on the performance of the model, especially on unknown data. The reason I mention this philosophy is because I often find students who are coming from really academic backgrounds, or maybe they've done machine learning in another programming language like R, they often request features that are just not available within scikit-learn. Things like really diving deep into model parameters. But scikit-learn is really focused on just quickly fitting and understanding and training a model, and then checking its performance metrics. So academic users who may be used to R-style reporting may also want to explore the stats models Python library if they are interested in exploring more statistical descriptions of models, such as significance levels in a linear regression. Now let's quickly review the framework we just discussed of scikit-learn for the supervised machine learning process. We will quickly see how the code directly relates to the actual process theory we described in the machine learning overview section. Recall from our discussion on the supervised machine learning process that we need to perform a train test split for supervised learning in order to fairly evaluate our model. And you can also recall that upon performing a train test split, you actually have four main components. You have the training set and the test set, and then with each of those sets, you have your X features and your Y label. So you end up with four components: X train, Y train, and X test, Y test. Scikit-learn easily does this split for us, which we're going to be using all the time with supervised machine learning. And later on, we're going to be learning about more advanced metrics and ways of testing your performance, such as cross-validation. But for right now, let's explore the syntax and framework for something like a train test split. The way this works within scikit-learn is you'll say from sklearn.modelSelection, So we have sklearn as the main library, and then we have model selection within scikit-learn. We're going to import the train test split function. And what the train test split function does is it takes in your X features, that is all of them, and all your corresponding Y labels, and then it creates the 4 components for you. And notice here, this is just tuple unpacking. It's returning 4 separate components. All your features for your training set, xtrain, all your features for your test set, xtest, and then the corresponding labels, ytrain and ytest. So we'll pretty much be running this in order to fairly evaluate our models. Also recall that at the end of the supervised machine learning process, the end goal is to have predictions, and then we want to compare them to the true y-test labels. So the way this works in general for scikit-learn is the following. And keep in mind, this is just a generalized example. The code shown here won't actually work if you try to run it. Basically, scikit-learn is formatted in the following framework. You'll say from sklearn dot and then some model family, such as linear models or ensemble models or tree method models, but some model family, and then all the algorithms that fall under that model family, you can import it from there. So we'll say from sklearn.modelFamily, import some algorithm. So we could say something like from sklearn.linearModels, import linear regression. Then you create an instance of that model. Also recall from our discussion on the supervised machine learning process that we could go back and edit parameters of our model. So we could define any specific parameters we want for the algorithm we're working with. So we create an instance of that model. Then, to train the model, you simply call myModel.fit and then pass in your training set data, xtrain and ytrain. Then you can easily get predictions. And if you want to compare your predictions to your known y-test values, what you do is you say myModel.predict, and then you can predict on your x-test sample, and you get your predictions. Then you'll say from sklearn.metrics, and you'll import some sort of error metric. Here, I'm just using error metric as a placeholder. We'll have a deeper discussion on various performance evaluation techniques and what metrics are important later on. But in general, the framework would allow you to import the appropriate error metric function, and then you would compare your known y-test labels to your predictions and understand your performance. And right here is the general framework code for essentially any supervised learning algorithm within scikit-learn. After a while, what you're going to be able to do is just quickly swap in and out algorithms and adjust parameters as necessary. And again, all we're doing is we're saying from sklearn, choose the model family, import that algorithm, create an instance of that algorithm with your desired parameters, fit it to the training data, and then predict on the test data. Then you want to understand the performance of your model. You choose the appropriate error metric, you import it from sklearn.metrics, and then you directly compare your predictions against your known y-test values to get some sort of performance metric. This framework will be similar again for any supervised machine learning algorithm. Let's go ahead and begin to explore it further by actually coding it out with linear regression. I'll see you at the next lecture.